Augmented reality creates an illusionary world by seamlessly blending the virtual with the real. However, this illusion is destroyed as soon as the user reaches out to touch the virtual and finds nothing but thin air. We present Annexing Reality, a tool to enable opportunistic annexation of physical objects from a user's current setting to provide a haptic experience for virtual objects. Our system allows content creators to a priori specify abstract haptic models for virtual objects. Based on the specification, the system optimally matches available physical objects to virtual ones, such that the overall visual-haptic mismatch is minimized. The task of annexation of reality can be separated into 3 phases. Model generation, in which a developer creates abstract haptic models for objects in the virtual scene. Object shape detection and matching, in which the system scans the environment and matches physical objects to virtual ones. Pose tracking and rendering, in which physical objects are tracked and overlaid with virtual content in real time. The developer first marks virtual objects that should be matched to physical ones and sets a priority for each. These priority values allow the developer to specify which virtual objects should be given higher matching preference when there are an insufficient number of physical objects available in the surroundings. Next, for each object, the developer starts by creating haptic models by manually fitting primitive shapes, similar to a collision model, over their graphical model. The developer then sets preferences for physical dimensions of haptic model components. By doing this, the developer specifies which physical dimensions of an object are more important in matching. As an example, here the developer has prioritized the radius of the cylinder matched to the handle. This ensures that the physical object matched to it will be small enough to hold in the user's hand. Minimum and maximum scaling limits are set to avoid unnecessary rescaling of virtual objects. The developer can create complex haptic models by adding multiple primitives to the virtual object. Finally, each primitive component of a haptic model is given a priority, indicating which one should be selected in situations where more than one of them match to physical objects. The haptic models are then saved, along with the graphical models, for use at runtime. Our system scans the physical environment, detects available objects, and recognizes their shapes. It first detects the dominant horizontal plane and connects field of view, then extracts 3D points of physical objects lying on the plane, separates them into point clusters, and finally recognizes the most salient primitive shape of each cluster. Each virtual object votes on detected physical object shapes based on their similarity. Note that the thicker arrows indicate higher vote values. The system allocates physical objects to virtual ones based on the voting. It uses the Hungarian algorithm to decide the optimal assignment. Our system tracks physical objects and overlays scaled versions of virtual objects atop in real time. It first estimates the rough 6D pose of each physical object by aligning a stored model to the scene point cloud. Then, a cubic volume of the scene point cloud is segmented such that it encapsulates the target object. Our system uses ICP algorithm to fine-tune the initial alignment and determine the accurate 6D pose of each object. It finally uses these poses to overlay the virtual objects onto physical ones. The system seeks to minimize the visual-haptic mismatch by rescaling the virtual objects to fit the matched physical objects. These are some of the other sample haptic models created by participants in our developer study and matched physical objects. In this case, the handle of a virtual lightsaber is matched to a salt container. Note that the system has chosen the salt container over the baseball bat, based on the developer's specification. In this example, the lampshade is matched to a bucket. Note that the system has chosen a bucket over the globe or balloon, as the developer has set a higher priority for the cylindrical part of the haptic model. In summary, we presented a system that allows augmented reality content creators to specify adaptive haptic experiences for virtual scenes. It opportunistically finds physical objects from a user's surroundings and uses them as props for the virtual ones, providing tactual sensation with minimal visual-haptic mismatch.